Alright, this is my jumping man problem. So the idea is that you have a guy who sits at the number line, and he's jumping a random distance between 0 and 1. And what he does is, so let's say he lands all the way over here. So he has a good jump, 0.8. What he's going to do is, since he hasn't crossed 1 yet, he's going to try and jump again. So he's going to jump a random distance between 0 and 1. So let's say he jumps over here. And now he's landed at 1.3. Now that he's crossed 1, he has jumped 2 times. And imagine him doing this a bunch, right? So let's do it again. So let's say this time he jumps and he lands, I don't know, here, right? 0.3. Let's say he jumps again. And this time he only does a jump of 0.4 and he lands at 0.7. Well, he's going to jump again. Okay, but let's say he does a really long jump. Oh man, he jumps all the way over here. He's now at 1.9. Or actually, no, he's now at 1.6 because he made a 0.9 unit jump. That took him 1, 2, 3 times. My question is, if you were to repeat this process over and over, what would be the expected amount of jumps, or the average amount of jumps that it would take for him to cross 1? Now, what we can do is we can look at what this means mathematically. Essentially what we're doing is we're picking distances, which I'm going to label as x1, x2, etc. And we are arranging them, basically adding them together, and seeing when we break 1, when we become greater than 1. So our base case, our basic, just kind of unimportant case, is when x1 is greater than 1, because this never happens. So we don't have to worry about our base case. However, x1 plus x2 being greater than 1 is absolutely possible. We already saw it. And same goes for it happening in 3 jumps or in jumps. And so in order to find this expected or average value, what we do is, for any expected value for a random variable, I'm going to call the random variable being j, the expected value is equal to the probability of it. In this case, we just have integers, so the probability of it being 1 times 1 plus the probability of it being 2 times 2 plus dot 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 all the way to pn, and we'd add up to infinity, because in theory there could be an infinite amount of jumps, or as many jumps as we wanted. And so what we have here is the expected value for the amount of jumps that we need. However, we need to find what this p-value is. What is the probability of it being 1 jump required? What is it the probability of it being 2 jumps required, etc. And so we know, base case, probability 1 is 0. We already know this. That one's easy. But what about probability of 2? Well, I know a lot of this may look intimidating, what I have drawn up here, but it's really not that bad, because what we have is, we know that when it takes 2 jumps, that means that x1 is less than 1, but x1 plus x2 is greater than 1. And I drew that area given in yellow. Now, the green is when x1 plus x2 is equal to 1. And so the red, being the unit square, encompasses everything. So in order to find when x1 plus x2 is greater than 1, we take outside the green into the yellow, but inside the red. And that leaves us with this yellow area. But a way to actually find the numerical value is to take our red, which is the area of the square in this case, minus the blue, which is the area of this triangle. And that gives us P2, which is 1 minus 1/2, or we could call it 1/2. But I'm going to leave it that way. Now, this may look kind of unnecessary, right? You can just, the yellow is, 1 times 1 times 1/2. It's pretty easy. And just say that P2 is 1/2. But as we get to the higher dimensional examples, you'll see that it's not quite as easy. So let's move on to the n equals 3 case, 3 dimensions. So what we have, and this is where this becomes very important. x1 plus x2 has to be less than 1. This means that after the second jump, we are still behind 1. Because in order for it to take 3 jumps, that would imply that the second jump did not pass 1. So this case is very important. Now, that is what I put in red over here. So we have our coordinate grid with x1, x2, x3, evenly distributed. They're all values between 0 and 1. And this volume we have encased here essentially encases all of the x1 plus x2 being less than 1, but still technically both of them are greater than 0, between 0 and 1. And the blue I have is actually when x1 plus x2 plus x3 is less than 1. That is the blue. And that makes sense because the green here, which is essentially when a plane, the plane being this plane, intersects through this cube and cuts it. And the plane cutting the cube essentially makes it so these values sum together are equal to 1. But we want when they're greater than 1, summation is greater than 1, but the x1 plus x2 is less than 1, which means that we want to be outside of the blue but inside of the red, or what I've labeled in yellow. Again, same idea. And again, what we do is we take, instead of an area, we take a volume. So the volume of the red is going to be its base area, 1/2, times its height, 1. Because it's just a normal prism. And when we do that, we can see that the red area is 1/2. Now for the blue pyramid, we take 1/3 base times height, which in our case is just equal to 1/3 times 1/2 times 1, which is 1/6. And so we get that the yellow volume is equal to 1/2 minus 1/6, which we could solve and say is a third, but I'm going to leave it as 1/2 minus a sixth. Now, we can continue with this idea into 4 dimensions and eventually n dimensions. So for 4 dimensions, what we end up having to realize is that because we cannot visualize it, we need to use the process we've been using in these higher dimensions. And so what we find is our red volume, right, which is when x1 plus x2 plus x3 is less than 1, that is essentially this pyramid. So the hypervolume is going to be this pyramid volume, which I'm going to call V3, times 1. And so the red volume, or hypervolume, is V3. For the blue, we get that the summation of the x values gives us something that is less than 1. And essentially, this forms some kind of hyper pyramid, you could call it, where you could almost imagine this is your, this is your x value, your y value, your z value, and then some kind of other variable. Some people use w, this 4-dimensional connection between these 4 points. Now, the blue volume you could just call V4, right? Where Vn is essentially representing our n-dimensional pyramid with points at basically 1, 0, 0, 0, and you have 0, 1, 0, and 0, 0, 1, and etc., etc. And so our 4-dimensional yellow is the same as before. It's going to be our V3 minus V4, which we will figure out in a moment. So the question is, what is Vn? Right? So we've labeled Vn as the volume of the n-dimensional pyramid. So here's what's going on. We know that for Vn, it's inside of this function, right? Where all x values are between 0 and 1. And so what you end up with is that you can essentially write Vn as the integral of Vn minus 1 as a function of h integrated throughout the height. So just as you could find the volume of this pyramid by integrating some base area through the height, which I'm labeling the height as top to bottom because it's a lot simpler, you're integrating it through the height, and you have these little, basically, in this case, it's just little triangles, which I've labeled here. They both have side length h, and you're integrating that area through the height. And the area turns out to be V2, the volume of this 2-dimensional pyramid, times h squared. And this is because it's 2-dimensional, and it is essentially each length on it is proportional to h. And so, or is equal to h. And so when we apply this function of h, what we do is we have Vn minus 1 of h, and this is equal to Vn minus 1. And as in the 2-dimensional case, we can represent this function of h as just the original volume multiplied by the scaling factor. And all of the lengths are equal to h, and so in essence the volume is going to be scaled by h to the n minus 1. And so what we do is we take this function of h and we integrate it with respect to h, and so we end up with this equation. And because Vn minus 1 is a constant, we can take it out and integrate h to the n minus 1. Now, using the power rule, this is equal to h to the n over n, and when we evaluate between 0 and 1, we end up with Vn minus 1 over n. Now, for those of you who aren't fluent with calculus, that may seem extremely complicated and intimidating, but the takeaway is this beautiful thing right here. Because what it tells us is that the volume of an n-dimensional pyramid is just the previous volume divided by n. So what's great about that is if we know a base case, we can use induction to find each subsequent case as we go into higher dimensions. For example, what we end up with is that v of 2 is 1/2. We already know this. You draw the triangle, whatever. v3 is going to be 1/2 divided by a third, which is 1 over 2 times 3, or 1 over 6. We've already seen this. But v4 is going to be 1 over 2 times 3 divided by 4, which is 1 over 2 times 3 times 4. Which tells us that if you see the pattern, v of n is going to be essentially, by induction, 1 over n factorial, which, as this guy shows, is such a surprising result. Now, using all of this, what we are going to do is, in our four-dimensional case, we can say, okay, well, v3 is just 1 over 3 factorial, and v4, 1 over 4 factorial. And when you subtract them, you can write this as 4 over 4 factorial minus 1 over 4 factorial, which is 4 minus 1 over 4 factorial, or 3 over 4 factorial. Now, what about for n dimensions? All right, so what we've got going on is that we will take p of n, which is vn minus 1 minus vn, which is equal to 1 over n minus 1 factorial minus 1 over n factorial, which equals n over n factorial minus 1 over n factorial, which is n minus 1 over n factorial. Now, if you plug this into your expected value equation, we end up with p1 times 1 plus p2 times 2, etc., right? And when you plug in this into your pn, right here, or right here, you end up with p1 is 0, p2 1/2, or 1 over 2 factorial, I really should write, times 2, plus 2 over 3 factorial times 3, plus, and it continues, n times n minus 1 over n factorial. Now, n times n minus 1 over n factorial, n over n factorial is 1 over n minus 1 factorial, but 1 over n minus 1 factorial with n minus 1 over it is just 1 over n minus 2 factorial. And so, in essence, what we're doing is we're just summing up the reciprocals of factorials. And as many of you have seen before, if you sum up 1 plus 1 over 1 factorial plus 1 over 2 factorial, etc., you end up with the beautiful mathematical constant E. And so the answer for the expected value of jumps, or the average value you get for the jumping man problem, is E.